we're asking them voluntarily to reach these extra targets to be good citizens, and there'll be this very nice side effect if they help make the technologies that we all need to decarbonize the electricity system much, much cheaper.
Hello, and welcome to Environment Variables, brought to you by the Green Software Foundation. In each episode, we discuss the latest news and events surrounding green software. On our show, you can expect candid conversations with top experts in their field who have a passion for how to reduce the greenhouse gas emissions of software. I'm your host, Chris Adams.
Hello, and welcome to Environment Variables, where we bring you the latest news and updates from the world of sustainable software development. I'm your host, Chris Adams. When we talk about the sustainability of software, because it's often not practical to directly instrument every single server, laptop, and mobile phone used to access a digital service, we end up using models all the time to help us make informed estimates about what the energy consumption might be at various parts of the supply chain. For example, the organization I work for, the Green Web Foundation, publishes a software library, an open source software library called CO2JS, that provides models for estimating the energy and carbon impact of basically using and creating web pages that we all use on a daily basis. That also contains open data about how green the grid is in various parts of the world, thanks to a collaboration with electricity maps. Elsewhere, the Green Software Foundation maintains a special carbon-aware development kit to give you an idea of the impact of running different computing jobs in different parts of the world and at different times, and even helps you automate some of those decisions when you're designing and architecting your own systems. And if you work with AI, CodeCarbon and EcoLogits are common open source tools for modeling the environmental impact of using and building AI services that you might be responsible for. So these work for planning how you build software. But if a significant part of the impact of software comes from the power it consumes, then really we need models for the underlying electricity grids as well, because how that changes in the coming years will have a huge impact on us no matter what we do. For this, companies and governments rely on grid modeling software that, as it suggests, models the cables, the power plants, the substations, and even some cases the data centres in the region to help people understand the impact of introducing new energy technologies or even staying with the fossil fuel default in some places. And when companies like Google make big, ambitious commitments, like powering every hour of their consumption from all their data centers with carbon-free power every hour of the day by 2030, it's underpinned by analysis from models like the ones we're discussing right now. These are done to check that it's actually doable. Arguably, the most popular open source project in this world is PyPSA, Python for Power Systems Analysis. And I'm happy to be joined today by Professor Tom Brown, who wrote the first version of the project about 10 years ago and continues to lead the project today to learn more about it and to help us learn more about the field around it. Tom, thank you so much for joining us. Can I give you the floor to introduce yourself today?
Hi, Chris. Great to be here on the pod finally. Yeah, my name's Tom. I lead a group of energy system modelers at the Technical University of Berlin. And one of the things that we do is develop software, Python for power system analysis, for doing this kind of grid modeling. So we do the software development, but we also do research with it. Because that's kind of what the tool is there for, is this analysis of how the power system works today and how it's going to look in the future. So you can give us some kind of demand. It could be a country's demand or a data center's demand, and then the software will try and tell you what the best combination of wind, solar, battery, or backup generation will be to meet that demand. And we could do it under various different circumstances. We can say we want super high reliability. We want to make sure we cover the demand in every hour, regardless of the weather conditions. And we can also set conditions like we want to be completely carbon free in the system. Cool. So I guess you have some software developers on your pod. So it's basically optimization software. So we have an optimization program that tries to minimize cost based on a whole lot of constraints.
Cool, thank you. And this is it's Python and open source with like MIT license or something along those lines?
Yeah, so we started with GPL because we wanted to be kind of pure. And we realized that was somewhat of a hindrance for some of the people using it. And this use case where you would publish the binaries without the code was kind of unlikely to occur. So we switched over to an MIT license, yeah.
Okay, all right. Now, Tom, I should probably just touch on, because you're a personal friend of mine and we've known each other for a while. And I just realized actually where we met, I think it was in 2018, when I was organizing an online community called Climate Action Tech. We were running these open calls called Clean Coffee, which were basically a bit like a kind of agile coaching technique called Lean Coffee, but specifically talking about sustainability and software. And I think you joined one of those. I think that was the first time I spoke to you, right?
Yeah, absolutely. It was. Yeah, that's almost 10 years ago now. It makes us feel a bit old, doesn't it? Well, I thought if you guys are doing green software and we're doing software for green energy, then there might be a few connection points there.
And that was the first time. Was that really the first time you'd actually used Zune? I think
that's what I was going to say. I think I was trying to remember back why that was so significant, but I guess before then we'd only used Skype for kind of one-on-one calls, and this was the first time it was really kind of Star Trek with multiple speaking heads on the screen, and it was kind of like a wow moment for me. And then I guess 2 years later we all got used to it in the pandemic.
Yeah, whether we like it or not, that kind of, it just became a daily for everyone's life to be mediated through those little squares. Okay, so you were working, and back then, I think you must have had the first release of PyPSA out the door by then, or you'd published the first paper to explain how it works or the thinking behind it, right?
Yeah, that's right. So I think we went back to look, and the first Git commit was at the end of 2015, and then we announced it on various online fora in the beginning of 2016. So it's really now just over 10 years old, the project.
Blimey, wow. And like you've done stuff before then, like previously, before you were working in open source grid modeling software, I understood you were working like with math, string theory, right?
Yeah, that's right. So my kind of like training is in math and physics, and I did my PhD in string theory, trying to unify gravity with quantum mechanics, which is not easy. At some point, it's also not very useful, right? I mean, it's mainly applicable in the center of black holes and back at the Big Bang. Those are the kind of main application areas, and that was at some point not super satisfying for me. So I went into the energy industry, and I was very fortunate actually to be able to work as a consultant doing this kind of grid modeling for 3 years in Darmstadt at a company called Energy Nautics. And there I witnessed that, open source is really not standard at all. So from the physics world, we were all very kind of free software. We put all our ideas out there. We want other people to use them. But this grid modeling world was very different. A lot of proprietary software and a lot of very politically impactful studies being done with no transparency whatsoever. So we did a big grid study for a high share of renewables in Europe in 2030, actually a kind of target that we might actually meet now. It seemed a bit wacky 15 years ago. And we saw that we needed lots and lots of grid reinforcement, like we needed these big cables going from the north of Germany to the south of Germany. But this was somehow controversial, and we were in meetings where people were shouting at us saying, no, those lines are not necessary, or those lines are only going to be used for coal energy. Mm-hmm. And it was kind of clear to me, this kind of arguments of like, my model says this, your model says that, just wasn't really going to help us have these important discussions unless we were really transparent about the assumptions, the code that goes into the models, the data that goes into the models. And that was then for me an impetus to go back into academia and develop the tools and also push on the open data so that we can have these discussions about how we're changing our system in a really kind of transparent way.
Okay, cool. So you just spoke a little bit about, wow, I didn't realize that 10 years ago you were actually having to fight those fights, because it's kind of taken for granted now. Like for people who are not familiar with the German electricity grid, about half of Germany's power comes from renewables, and the north of Germany is really, 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 really windy. And we've got like offshore wind and stuff like that, but lots of the industry is in the south. So the idea that you wouldn't have like the connectivity, and this is something that you would need. Wow, I just assumed that was like common knowledge, and you had to fight this. And then having models at least spells out to say, no, folks, this is what's going to be happening, and this is why. And I guess, is it a bit satisfying to kind of see, I told you so, here's the commit SHA from like 2016 or something like that as well?
Yeah, it's complicated. Like we definitely need to build grids. One can overbuild grid as well, and that can lead to high costs. So you have to kind of get the balance right. And I think the message that grid expansion is very valuable to the system because it lets you kind of balance the wind resource. Like when the wind is blowing really strongly in the UK, they can export it to the rest of Europe and vice versa. That's actually what the grid is really, really good for. But you shouldn't go too far either. If you build too much grid, then you end up putting a lot of costs on the consumer. So finding this balance is really right. But this point was somehow controversial back then because there were people pushing really hard on very, very decentralized systems where every region is kind of balancing all by itself with storage. And I think definitely storage is now playing a much bigger role even than we realized back then. But you do need a good solid grid also for the balancing role.
I see. And like basically the idea behind having open models allows you to have like a data-informed discussion like this. And I think we've seen some examples of this actually most clearly. I mean, I think in the last few years, there's been a whole push for hydrogen as some kind of like chemical molecule fuel rather than just like relying on renewables. And my understanding is that in order for certain projects to receive subsidies, there is now a real kind of impetus to have some kind of modeling to back up what you're saying, somewhat like you were describing here, so people can challenge that and people can understand what the underlying assumptions for any of these massive projects, for example.
Yeah, so there was a push for some of these hydrogen projects to have kind of open and transparent cost-benefit analysis done for the projects, and we're pushing quite hard in this discussion at European level for the centralized planning processes that go on in Europe for grid infrastructure and for pipelines for hydrogen and gas, that this is also done as openly as possible because they're just changing the system right now. So we think it's really important that whatever happens, there's at least transparency there so everyone can see the assumptions, but also reproducibility. So if I have some cool new technology to increase the capacity usage of a transmission line, like maybe I adapt the capacity to the ambient weather conditions, or I have some cool new tech for long duration energy storage, I can take the model and show that things could be done a bit cheaper. And I think it's only by having that kind of big multiplayer discussion that we can find the best ways forward. Because I mean, we should keep underlining this. This is a crazy transformation of our energy system. We're going from like a fuel-based system with lots of emissions to one based on varying wind and solar and a ton of storage. And it's a huge, huge change in a system that was not built for it. And we don't know exactly how the best way to do it is. We're kind of learning by doing on the job a little bit. And we keep having ideas and then correcting. So if you look at the discussion 5 years ago, there were a lot of people pushing strongly on green hydrogen. We were also definitely in the model seeing some role for the green hydrogen. And now we're kind of realizing that we can actually electrify many of those applications, and probably the role is a bit smaller. And that's an adjustment just inside of 5 years. And we can make those adjustments quicker if we're transparent about the results and we learn and then can move forward.
I see. Okay. I'm really glad you shared some of that extra and you also expanded on some of the grid discussions, because for people who might not be that familiar with how electricity systems work, the cost of grids tends to be socialized across everyone rather than like the generators. And that can be one of the reasons why you're seeing some pushback from people basically arguing against data centers right now, or arguing about data centers, because these are new, extremely large loads on the grid that often require a degree of improvement of the grid or investment in the grid that there might not have been previously. But one thing I learned from you was that, okay, there is a bunch of this happening anyway, but there still is something that we need to take into account, because it may be increasing the need in certain places just because you have such density of demand. I mean, maybe we could talk a little bit about like the role that data centers come in, and if there are any kind of examples of this, because I believe that you folks did a bit of work with Google, back, all those years ago, to see like, is 2030 possible, for example? Maybe you could expand a bit on that.
Yeah, that's right. So, I mean, a lot of what work we do is looking at Germany and the transformation of the European system, but we've also done work for Google in this case, because they were interested in the impact of an hourly matching strategy for their power procurement. So kind of what the standard was beforehand was that you do this annual matching, which I think you've discussed on your pod before, but just for your visitors, if you have this, just for people who don't listen to every single podcast, if you do annual matching, you have this kind of crazy situations that I can match my data center, which is maybe running in the winter in the evening, with a whole lot of solar power that's only generating in the summer in the daytime. So you're only matching the volume of the electricity that's generated if you're annually matching on an annual basis. And that means you have a big disparity between when it's being generated and when it's being consumed. And you even have a disparity in the location as well. So you can offset your generation in Germany with hydroelectricity in Norway. And that's hydroelectricity that may have been built 40 years ago. And so that's not really what common sense understanding of matching would be. And so Google wanted to investigate if we do this hourly and locational matching and insist on new generators getting built for that, what the impact would be. Because that aligns much more with people's common sense understanding of matching, that you really try to match when the electricity is being consumed with when it's being generated from clean sources. And when you do that, when you go to an hourly matching metric, then you're also not just stuffing solar into the grid whenever there's already lots of solar there, which isn't very helpful because then the solar ends up getting wasted because there isn't enough demand at midday to absorb it. But you also then start looking at storage technologies, for example, that can start shifting that excess solar in the midday into the evening hours as well. So it starts to make you think a bit more system friendly, like a good citizen, to make sure that you're covering your demand and not actually increasing the peak demand. Because what often happens when data centers come in and just match with wind and solar is they match the energy, but they're actually increasing the peak demand in the system. And that peak demand in the system then has to be covered by conventional generators. But if you try and do your procurement so you're also covering at that peak, then you're being a good citizen and not contributing anymore to the system peak that then has to be borne by the entire system. And by the entire system, I mean other consumers like you and me. So there's an attempt to get something a bit more aligned with common sense, where we're really doing the accounting to match our consumption.
Okay, thanks for that. There's a couple of things that I'm going to try and pull out to make sure I understood. So the first thing was you were talking about matching power, like say solar versus wind, and I assume you're referring to the idea of the fact that when you make a claim about green energy, or let's just call it green energy for now, it's essentially the idea that a certificate from a certain time. So you will basically say, I am using green power, I'm using power in winter, but I'm using certificates from power that was generated. That's like the claim that you're talking about here. So this hourly or location-based approach is saying it's a bit silly to claim that using data centers at night in winter is being powered by certificate or is being made green because you're applying certificates from summer during the day. But instead, it makes more sense to be saying, well, if I'm going to be using a data center in the evening, then really I should be looking at something like wind, which is plausibly running, or it's come from some kind of battery, for example, that are then being discharged to power that data center. That's what I think you're referring to there, right?
Yeah, exactly. Or it might encourage you to look for some kind of dispatchable generation, like a geothermal plant that can also then run in that winter when maybe the wind and solar aren't available. So it gives you a kind of broader set of technologies, because we do need to get the whole system decarbonized, not just the windy hours and the sunny times at midday. So it starts making companies think in their procurement about a broader set of technologies to get all the way to zero emissions in the power sector. And it doesn't mean that you have to do every single hour to 100%. So there's various stages of this, and probably it makes sense, first of all, just to do the accounting this way. This is what the reform of the greenhouse gas protocol is about, is just to get sight on what's going on in the system so we know roughly where we are. And voluntarily, then companies can try to go a bit higher. So maybe a data center today matched with wind and solar is maybe covering 60% of their hourly demand with wind and solar. And then maybe over time, they edge up to 80 or 90. Probably getting all the way to 100% is tricky, given the timelines, but we can start edging people up to 90 and 95%. And then that's really good for consumers and the overall system as well.
Okay, and you said another thing that, if I may, that I really want to touch on, because this is something that I think a lot of people overlook. You were saying about how data centers, they essentially make peaks a little bit peakier. So because there are significant fixed use of power, when lots of other people are using power, that essentially pushes the peak very, very, very high. And that means that in most markets, rather than say the price of electricity being set by say wind or solar, it's being set by gas, and that tends to be quite expensive. And like we might look at say Europe as an example, where over the last few years you've seen Spain with very, very low electricity prices compared to other countries of if you look at say Spain and Italy, for example, they're more or less the same latitude, I believe, or they're comparable there. And Italy has gas setting the price a lot of the time, and as a result, its electricity prices are very high. And we've seen the same thing, whereas for Spain, because they have actually invested significantly in not having gas at that price to kind of have something else meet demand at the peak. You've ended up with much lower electricity costs. Is that what you're referring to there, right?
Yeah, partially. I mean, it's all part of the same story. I mean, if you increase the peak demand, you need to also buy extra generators to cover it. I mean, that's a problem that you see in countries like Ireland, where you have a very large share of data centers in the demand, and they start really altering the kind of fleet that you need to cover the demand. And it also puts in danger the decarbonisation targets. You have almost a quarter of electricity demand in Ireland as data centers, and it could go up to a third in the next couple of years. If you're increasing the demand massively, then all the electricity targets of decarbonising their electricity become much harder with all the extra demand, and they also need to meet that peak demand. And what you're saying on prices is a very general thing, that we see much higher prices in Italy because gas is setting the price more often, because they didn't invest in wind, solar, and batteries as Spain did. What's also really helping Spain, apparently, has been a very good hydro year as well. So they've had lots of water filling the reservoirs that can then be used for generation. That's also really helped decrease the prices. But it would really help Italy for the price situation if they built more wind and solar to displace some of that gas. And that's one of the things they can do. And it's kind of maybe a bit orthogonal to the data center question.
I see. Okay, I realise. I'm glad you mentioned about that. You mentioned Ireland, for example, because there's some. There was, I think, a couple of weeks ago, there was some analysis released by Friends of the Earth, who basically looked to quantify how the cost of essentially making the peak year of data centres, how that reflects the cost of energy kind of across all of Ireland. And it's a non-profit organisation, so they have a very specific agenda. But generally, the main takeaway was that this is adding a few €100 to the cost of every single person annually for this, because you have gas basically setting the price like this, like you saw with Italy, because this new inflexible load is changing the kind of nature of the grid, basically. So this is one thing that we're able to see with like kind of grid modeling, for example, to like, and that also kind of points us to things we could do differently. For example, we could say, well, if we don't want the peaks to be really, really peaky, then it makes sense to have some way to either make the loads more flexible, make data centers more flexible if they're going to be part of that, or find a way to not be relying on, say, burning gas, for example. There's maybe other options that you could plausibly do to stop shifting costs to people in that way, right?
Yeah, absolutely. And probably orthogonal is not quite the right word, but if you do have that extra demand, and if you don't make any other changes, it will mean that the gas is more often price setting. So actually, you're totally right there. And on this demand shifting perspective, when you do this hourly matching, you also get this incentive to be flexible in your demand. So you may actually try to reduce the demand a little bit in those hours when there isn't that much wind and solar or other carbon-free electricity on the grid. So it actually gives you these incentives. And my colleague, Igor Riepin, who led this modeling work for Google, he did this very cool study, and I think you had him on the pod as well, where he actually looked not just at people using this flexibility in time to shift jobs around, but using it in space. And there's a very cool study, because if you have a set number of jobs for a large company like Google, you could, if they're not too time critical, you could start moving them around in time and in space as well. So if it's very windy in Ireland, you could move all the jobs to Ireland. And if it's very windy in Germany, then vice versa. And this really, really helps to reduce the cost of meeting these hourly matching demands.
So I'm really glad you mentioned Igor. I really enjoyed that post. We'll share a link to it in the show notes for this, because there's one thing that he mentioned that kind of blew my mind, was that wind systems move. So you could plausibly, he was explaining how you could actually have, say, a bunch of data centers or a bunch of software jobs catching the wind in Ireland, and then maybe a few hours later, because the wind system has moved across Europe, you can then catch it again in, say, data centers in Germany or else, for example. He said, like, there is, he was explaining how you can model the space behind this so that you essentially can have jobs follow the wind in this way to kind of to make the most of the clean power that's around. And that's so different to a fuel-based system, which is entirely like static. Yeah, that's
and
like.
This is, by the way, related to what we discussed at the beginning, this grid stuff, because these weather systems, they kind of come in off the Atlantic and they move kind of quite slowly. It maybe takes a couple of days to cross from Ireland over to Germany. But what this means is when it's sitting over Ireland, it's blowing really strongly. And then you can build a transmission line to move that wind eastwards towards Germany. And then when it sits over Germany, you can use it in the other direction to move all that wind energy with the transmission cable back to Ireland. So you can use the transmission in that way, or you can basically move the demand instead. So it's like a kind of virtual interconnector, people have called it, where you just move the compute jobs around correspondingly. So you can use basically the compute jobs being shiftable as a kind of substitute for the transmission. Thank you.
I'm really glad you explained that part there, because I have almost zero understanding of like wind systems or anything like that. And like when Igor told me that was just incredible for me. The idea that like obviously you know on one level it works, but to have it actually show up in a system like this in a way that you might plausibly catch as a practitioner was kind of it kind of reintroduces notions of like, I don't know, seasonality, but for like internet speed,
Yeah. And it's really cool. We really see it happening. We have these big transmission lines that go east-west between Britain and Denmark, between Britain and France, and so on. We really see them being used in this pattern. And maybe this also connects a bit to this general variability, like this multi-day variability from the wind is one reason why batteries on their own don't really get you through to 100% carbon-free energy, because you have these periods with low wind that maybe last a couple of days, and then a battery maybe gives you a couple of hours, and that isn't enough to bridge the difference. And it's one reason why it's maybe a bit easier to get to 90% than 100%, because you can get to a 90% with wind, solar, and battery, but that final 10% means filling in those, especially winter periods with low wind and low solar that can last multiple days, and that then gets kind of difficult.
I'm glad you mentioned this part here, this last 10%, because that's a nice segue to talking about some of the uses of modeling software that might impact how we talk about, like how we might think about either supplier choice or how we might think about decarbonizing data centers. Because as I understand it, there's a few kind of named effects that we've been describing. So one of these is this idea of like, I think there are two named effects in a paper that was published by yourself and Igor. So this notion of volume, with the idea being that one of the ways that a 24/7 approach to looking at the grid helps is that you increase the volume of total electricity available, for example, of clean electricity available. It may be cases where you have more than you need, for example, that, like as you described, can be shared to either neighbors or even distant neighbors, like the example you described between Germany and Ireland, sharing electricity back and forth. But there's also this profile idea, the idea being that if you want to, say, keep a target, then you're going to shape your own consumption to the local availability of clean power as well. But there's one thing that I think you hinted at, this notion that there is like an innovation driver as well. Like, because where there are certain technologies which are very mature, like say solar, for example, but there are some technologies which are not so mature, like maybe longer lasting forms of battery, like say iron air battery and stuff like that. Essentially there's a kind of driver to, if that you have enough people purchasing it, that brings down the cost to make it more economically viable compared to the alternative, right? Maybe you could talk a little bit about that part there, because I think that was something that you've done some previous research on, and that has bearings on getting to those last few percent, for example.
Yeah, it really, really does. So, I mean, obviously, if you're hourly matching your data center, then you're not consuming fossil generation in that cold winter period with low wind and solar, because you've made this effort to cover that demand. That's the kind of profile effect you were saying. But actually, because you've been now investing in new technologies, so batteries are not particularly new, but if you're trying to get to 90 or 95%, you might have then made an investment in a longer duration storage. So a new kind of technology that doesn't just store for hours, but you mentioned iron air. Form Energy, for example, produces these batteries that go for 100 hours, and that could then plausibly get you through this multi-day period with low wind. And these technologies at the moment are a little on the expensive side, so they wouldn't necessarily be cost optimal for the overall system. But if Google decides to, or another company decides to voluntarily go for a high target, then they start investing in this technology. And we have this effect that we've seen for solar and batteries, that the more you build, the more the manufacturers get experience learning how to do it more cheaply. They have more energy efficient ways of doing it. They build the factories bigger, so you get scale effects, and then the cost comes tumbling down. And we would expect to see this if some companies start voluntarily meeting these hourly matching targets, that we see a lot more investment in long duration energy storage, in advanced geothermal. And then this pushes these technologies down the learning curve. It's the kind of language that they get much, much cheaper, like we've seen for solar and batteries. And then suddenly you get a deployment in the rest of the world. And that unlocks a whole lot more decarbonisation, like way more than what Google is avoiding or some data center is avoiding in its emissions profile. It's now making decarbonisation viable for the whole system, so all consumers in Europe, in India, in China, or wherever. Because, when we made solar cheap, Germany and Italy and other countries were involved. They were paying lots of money to build solar in their countries. And they made some dent in the emissions in Germany and Italy, but the main thing they did was make solar cheap. So we're seeing this huge solar boom worldwide, and that probably would have come 5 or 10 years later if there hadn't been a big push by Germany and Italy to be leaders. So if we ask our data centers to be leaders in this area, and you could ask, well, why are we forcing data centers to make special efforts here? But it's because they're bringing these huge extra loads into the system that threaten to swamp some of the systems like Ireland or elsewhere. And they have the potential also to make it much harder to reach the decarbonisation targets. So we're asking them voluntarily to reach these extra targets to be good citizens. And there'll be this very nice side effect if they help make the technologies that we all need to decarbonize the electricity system much, much cheaper. And that could be the really transformative catalyzing effect of 24/7 commitments.
Okay, let's put some numbers on this, because there's a few things like we can actually some of this can actually be quantified. So as I understand it, we've got something in the region of, at this rate, probably between 600 and 700 billion dollars are being spent on data center build out just in this year alone, for example. And by comparison, that's like a meaningful share of all clean energy investment right now, right? Like if you assume that clean energy investments is like between 2 and 3 trillion each year, then 0.7 trillion just from one sector is going to have some impact here. And I think what you're referring to, this learning effect, there is, I believe it's called Wright's law, the idea that if you double the the quantity of any kind of technology, there will often be a learning rate which brings down the cost by a certain amount. And like solar, we've seen something between 20 and 30% every year for the last 30 years. And that's how something which was so expensive that only satellites could use, to something that you can put on your balcony now in Germany and now the UK, or even parts of the US, for example, as one example for this, right?
Or even in Finland. Like even in Finland, there's like solar panels going in. It's really crazy. Yeah, but this is this learning effect that if you double the cumulative capacity, like the total amount that you build, then you get maybe, it depends a lot on the technology. You could get 20, 25% for solar batteries. We don't know exactly what it is for iron air batteries or for advanced geothermal, but we can do these tests now to see how quickly the costs do decrease. And we're not talking billions that are necessary here. I mean, I think we calculated a couple of 100 million investments would already give us some sight on how the costs would evolve as more is built. So just taking a fraction of this money and putting it towards new technology would help us. It would increase like the information. It would increase our knowledge about how quickly these technologies will learn, how quickly the costs will come down. And that then gives a good signal whether it's worth investing even more in them.
Okay, I'm glad you mentioned both Form and Iron Air, and we're referring to this because, as I understand it, like PyPSA is an entirely open source project, so it's not just your research group that does this. There's one company I know called Open Energy Transition. They're actually did some work with Form specifically, and they actually do have open models showing how these kind of batteries integrate with the grid. So like there's data there for this. And I mean, the mention of Google is kind of interesting because in Minneapolis recently, Google did make a significant investment. They built the first ever, I think the first really, really significant deployment of an iron air battery like this in their new data center. That was, I think that's the biggest battery that they've ever created. And that's pretty much used up all of or the majority of the company's capacity to make batteries for the next year or so. So I guess we're going to find out in the next couple of years what that kind of change in learning might actually be. And my understanding is that these are some of these kind of learning rates. These are some of the things that are already that are inside PyPSA and some of the modeling things. So you can say, well, if we were to do this kind of investment, this is how much easier hitting fossil free by 2030 might actually be. And these are the kind of investments that you might need, or this is why investing in here instead of yet more gas might make more sense from a kind of longer term economic perspective, for example.
Yeah, that's right. So we had a commentary paper together with Igor was leading it, and Jesse Jenkins from Princeton and Devin Swayze from Google joined on that paper, and we did a few kind of not quite back of the napkin, as a bit more sophisticated, but we did a few relatively simple calculations that show that this effect of unlocking this learning and that then helping other places, we just looked in Europe, decarbonize, is probably much, much bigger than the directly avoided emissions. This indirect effect is much larger. And we could put these learning curves then into the PyPSA model to test that. And I'm glad you mentioned the Open Energy Transition study for Form, because that's kind of an example of what I was saying a bit earlier, what this open models unlock. It allows companies like Form to take the models and demonstrate at what cost points they would be able to really see very, very large investments. So they can judge for their own technology what price points they have to hit to see very, very large deployments. Then they can show that to other policymakers in a kind of trusted environment. And this is maybe not led, but I mean, it's one of the things in the discussion that have also led to government incentives and policy mechanisms to encourage long duration energy storage. So there's been policy measures, I think, in the UK to encourage long duration energy storage based on, not in the knowledge of some of this model showing that it's important. And maybe that's actually just another point. It's like, why should companies be solely responsible for innovation? Like the government also plays a big role in innovative technologies. And I guess the companies adds another string to our bow of a source of capital that can be pushing innovation. So governments are also doing this role. Governments are also pushing green hydrogen projects, green steel projects. They're pushing subsidies for carbon capture and storage, and they were the ones who were pushing wind and solar and batteries in the first place. But having a few companies, especially those with deeper pockets, do this is also very, very helpful, especially in these days when the governments have sort of not got so much fiscal capacity. They're kind of running out of money at the moment. So having companies also there doing this is really, really helpful for the global decarbonization picture.
And to be honest, it does sound a bit more socially useful than just companies buying their own shares, which ends up being a use of the money, right? So yeah, I kind of, as someone who is not a shareholder in any of these huge tech companies, but is definitely affected by them, especially if they're affecting the trajectory of like our global decarbonization, I would prefer to see them make clean energy cheaper for more people rather than this, because they seem to be doing pretty well themselves anyway. Yeah. They're making enough money as it is, right?
And they have a willingness to pay, because the cost of these AI data centers, the chips, is a much larger component of the cost. So asking them to maybe pay 10 or 20% extra to reach a 90% carbon-free energy target, I think is a totally reasonable ask, and do this way rather than just building a whole lot of off-grid gas generators, which some of them have been doing. So, and that's partly related to this grid connection problem, that they can't get grid connections, so they're going instead off the grid and then getting a gas connection and powering the data center with gas-powered engines or gas-powered turbines.
I'm glad you mentioned this part here, because this was one of the things that blew my mind when I was looking at some of the models and some of the papers that you shared. Like the costs I generally saw were between now and say 2030 to have like to meet maybe 90%, or like maybe you could share some ideas of like say like 80% or 90% like hourly, say fossil free, for example. I was seeing figures between 100 and 150 megawatt hours, and it goes quite a bit higher up in the last few percent because it gets quite a bit more difficult. But when we look at the cost that people sell kind of AI inference at, I mean, because we've seen X.AI, or now called SpaceX, make a filing for S1. We can see that Anthropic are paying them for basically the use of power. They're paying the equivalent to around $5,000 per megawatt hour. So this is right. And then that kind of really spells out, and that's what Anthropic are paying at cost, which that's not what they sell to us. So there's a margin on top of that margin that you could have there. So therefore, when we look at this, it feels like a rounding error to actually just use like proper decarbonized power, surely.
That cost is probably also covering the depreciation of the chips and stuff as well. Like that's probably a large part of it as well. But yeah, so I mean, when we were looking in our study, we're talking, just under 100 euros per megawatt hour for reaching a 90% target. And then it starts, it's like 100 euros per megawatt hour. So that's way below that 5,000, obviously. And probably those, in the US, it'll be a bit cheaper, especially if it's not decarbonized, because they'll be using the cheaper gas that's there available in the US. What happens is if you start cranking up from 90 to 95 to 98 to 99, especially in these northern latitude countries like Ireland and Germany, you do have these winter periods with low wind, and then you need to have either a lot more long duration storage or you need some kind of backup generation. So you could have a gas generator that backs you up for the last 3 to 5%. And if you want to decarbonize that, then you start getting a bit more exotic. You either have to start capturing the CO2 or using green fuels like green hydrogen to cover that missing bit, or you completely rethink and then go for advanced geothermal or something like that. And then you're talking maybe more than 250 euros per megawatt hour for that 100% hourly matching.
I see. Okay, so you're still in the kind of low hundreds, basically, when people are selling things at the low to mid thousands, essentially. So, I mean, as another data point, so there's a company that sells inference by the kilowatt hour. It's a company called Neuralwatt. They've been on the podcast before. They sell inference at 5 kilowatt hours it's $5 per kilowatt hour of inference. So that's enough, and you basically, you can use that to spend on any kind of model you want, right? Rather than kind of making guesses about tokens and things like that. And that is another data point, which also, when you look at $5 per kilowatt hour, that's $5,000 per megawatt hour. So again, that gives you an idea of like the fact that there is space. There is definitely like space in the budget to actually have cleaner power here a lot of the time. And you just need to look at the fact that in the same way when you have green steel in a car, for example, green steel might be twice the cost of regular steel. But if it's only if it's single-digit percentage in the cost of a car, then it's quite easy to absorb into this. And most of us would prefer to live in a habitable world, for example. So this seems to be like, there is space here in all these cases.
The major constraint really is just time. I mean, the reason that these data centers are going off grid and with gas connections is they can't get the grid connection fast enough. So we need to make sure that these grid connections are available. They just reformed the grid connection queue system here in Germany this year, so that projects are evaluated rather than first come, first serve, but by their maturity. And I think that's really, really important step forward. And we need to make sure that also the wind and solar permitting can happen quickly in order to meet all of this new demand as well. So actually, it's more of in some ways, the energy and the cost is not the constraint. It's the speed of the permitting and making sure all of this can happen quickly. Because if you just look at the energy cost numbers, it should be totally doable, especially for the data centers in this case.
All right, thank you as a literal professor of energy systems, being able to confirm some of this is actually quite helpful, because when some of us who are in like civil society say this, we may not have the same weight that you as someone who's leading this might be able to say. So that's actually quite helpful. So thank you for that. Now, if we just open this up a little bit more widely, we've been speaking primarily about data centers and decarbonization of data centers, and we've kind of established that there are some of these kinds of drivers at economic level, and as maybe a software engineer, we understand there are these effects like profile and volume, and if we think about carbon-aware programming, like let's adjust our use in relation to availability. That's something that we can, as developers, like do. But my understanding is that you haven't just been modeling data centers and just been modeling, like you've been looking at things more widely. And I can never remember if the correct term is 90-90-90 or 80-80-90 or something like this. But this is some work that you shared recently, which actually ranked pretty highly in Hacker News, and that might be how some people have come across some of your writing and some of your work, where you are modeling like transition of the rest of the energy system, for example. Maybe you could talk a little bit about that, because I found this quite exciting to learn about myself.
Yes, so it hit the top of Hacker News actually. This blog post that I did was looking at what it looks worldwide if you try to meet some demand with solar and batteries. And what particularly I was doing was looking really globally at every single location in the world, trying to meet 90% of a flat demand with solar and batteries, and then leaving some kind of fuel for the final 10%. So adding up all the costs of the solar panels and the batteries, and then including the costs for some backup fuel based on natural gas. And the particular thing about this is we really weighted it based on where the population lives. And most of the population in the world doesn't live at high latitudes like us. They're living much closer to the equator. So 90% of the population lives within 45 degrees latitude of the equator in this kind of sun belt. And there it's actually super reasonable to imagine a solar and battery world. So for half of the people, it's below 65 euros per megawatt hour. For 80% of the world, it's below 80 euros per megawatt hour, and 90% below 90 euros per megawatt hour. So most of the population now, or for 2030, we did the study, can get most of their power from solar and batteries and save money versus a fossil alternative. And that was the thing that really, I think, definitely blew my mind. When you really look where people live, solar and batteries are just going to eat up a lot of that electricity demand.
Wow. And like, you can say this, and this sounds kind of cool, right? From like narrative perspective, but maybe you could talk a little bit about, like, I mean, is there surely there's a quantitative basis behind this, or there's like is if someone wants to look at this, like, is there a model you can point to, or what? Maybe you could share. Yeah.
So we ran this model for every single pixel where people were living, or enough people were living, and then we ran a full year of hourly data. So we were looking for that full year of solar availability, how much solar and battery you would need to build to get to 90%. And then you have this fuel covering up the difference. So we ran this, I think, I've forgotten how many, it was like definitely in the tens of thousands of simulations for each of the little grid pixels. And you see just all of these countries in the middle. So that's, Southern Europe and all of India and Africa and large bits of Southern United States as well. They all have this super cheap solar and battery electricity. And if you add then wind into the mix, you also get very cheap at these higher latitudes as well. And this is just for 2030, assuming that costs will come down through these learning effects. And if you go to 2050, then you're just blown away by how you're dropping another 20 euros per megawatt hour for the cost as well. So we did I did lots of different variations of this calculation, and they're in a blog post, which I guess you can link from the chat. And we're actually seeing now huge solar and battery deployments everywhere. So this isn't just something theoretical that's in the model. It's really happening. We're seeing 600 gigawatts of solar being installed every year, and huge battery deployments. We have, even in Germany, huge battery deployments coming into the grid. And this will really, really start eating into gas demand and coal demand, and makes me a little bit more hopeful about where we're going with the energy transition.
Blimey. Wow, that's okay. We're definitely going to share some links to that, because that sounds, if you're looking for something to like act as a nice antidote to some of the news you see in the new on the daily, then maybe looking at this might be help, just understanding the shifts in economics that may not be celebrated on the daily, but are actually really, really helpful for understanding the trajectory we might be on for at least decarbonisation of this part. And can I just check one thing? You said, so like most of the world, this figure of like 90 euros per megawatt hour. Now, when I pay for electricity, I might be paying for, I don't know, something like between 40 and 50 cents per kilowatt hour. That essentially means that like there's obviously that this figure here basically means that the amount I'm paying in my bill is like there's that generation is a share. There's still share for like profit to pay people and to invest in grid and everything like that. So this is a figure which is actually plausible. Like I could see that. That's comparable to what the cost of generation on the kind of energy markets might be anyway, right?
Yeah, exactly. So it's really it's a production cost. It has a cost to connect the units to the grid. So it kind of stops at that point where the generation connects to the grid. So it's then comparable with what you might get from a gas generator or a nuclear generator. And what we see in Germany on the wholesale markets for electricity is futures prices. If you look for the price for electricity next year or the following year, it's in this 90 to 100 euro per megawatt range. So this is absolutely competitive with the future prices that we see in the German market. But for your end consumer residential bill, there's a whole lot of things that come on top. So your retailer has some margin. You're paying quite a big block for the network charges, as we were saying before, to pay for all the grid expansion. There's also taxes. You're paying VAT on top. You're paying an electricity tax on top of that as well. And there are a few extra charges in Germany as well. And so then you end up landing as a new consumer at maybe 3,000 euros 300 euros per megawatt hour. So you've kind of tripled the price compared to the wholesale price because of all these extra charges.
Okay, so the takeaway there is that the economics are actually quite plausible to move to a primarily fossil-free grid for most of the world, basically. Yeah. I am so glad there's data like that in the public domain, because from a campaigning perspective, being able to point to that and say, look, this is where you folks are. Like, here's the pixels that represented your population. That is exactly the kind of like nerd catnip that I think people might enjoy on this podcast.
It's really true, and this is actually based on an analysis that Ember did. So Ember, you probably know, is an NGO that focuses a lot on data around the energy system, and they'd done this for a couple of cities. And the main thing that we did was to take that analysis by Constanza Rangelova and Dave Jones, and we just applied it then everywhere. And I think they just released this morning a similar analysis as well. They did this kind of global analysis, and yeah, I think it's an important antidote to kind of a lot of the negativity in the energy space and generally in the world, just to remember that we're on course to have very, very cheap solar and battery generation. So in our research group, we have a mantra: if anything's getting too depressing, then we just say solar, batteries, electric vehicles. And we repeat this mantra multiple times, and everyone starts feeling a bit better. Because with those three technologies, we can just do so much. We can get a big chunk of those transport emissions, all of the road transport. We get the electricity emissions as well. And that gets us really, really far in our decarbonisation path.
Well, Tom, thank you for giving us all this, I guess, sources for hope and to be excited about some of these changes. Now, we're just going to come to the end of the podcast, and I want to wrap things up a little bit. But for people who have found this interesting and want to learn more about it, we're obviously going to link to your personal blog and the kind of this 90-90-90 thing that we're referring to, and also some of the other examples. But PyPSA is an open source Python project, right? So people could just check it out and rerun some of these analyses themselves in most scenarios, right?
Yeah, so I mean, it depends what you want to do. For the simple analyses, you can run it on your laptop. If you're doing a more detailed grid model for the whole of Europe, you're probably going to need a bigger machine with a little bit more memory. But yeah, all of that software and data is there. And I also don't want to give the impression that I've done all this myself. It's been a real team effort. So members of our team, Jonas Hirsch was there at the beginning, Fabian Neumann, Fabian Hoffmann, Lucas Tripper's taken over all the development now. Igor contributed stochastic optimization. And we have a very distributed set of contributors now, including companies like Open Energy Transition. And we also have a very broad set of users now. So Transition Zero's continues some of this 24/7 work. We've seen big institutional users like the International Energy Agency use PyPSA for their seasonal flexibility analysis, and even institutions in Europe like the Joint Research Centre of the European Commission using it for pricing analyses. So we're really seeing people leveraging these tools for all kinds of analysis, and that was the kind of innovation that we really wanted to unlock with the open source stuff. So if you go to the PyPSA website, you'll see a little introduction, how to use the software, and then also a ton of user examples where people have used this in studies. Also, not just in Europe, we've seen it being used in Canada and Japan, Korea, South Africa, you name a country, probably there's a PyPSA study that's been done with it.
Wow. And for people who think this is a really cool idea, but might not be quite ready to jump into the world of modeling things themselves, I believe you mentioned a project. You told me a story before we recorded about OpenStreetMap and how you thought that was never going to work, but then it turns out it did actually work out, yeah? Maybe there's this project, MapYourGrid, you can maybe just briefly just give a name check on this, because that may be one way for people to be able to contribute with it if they're not energy nerds themselves, for example.
Yeah, that's right. So I was at the Open Knowledge, I was participating in the Open Knowledge Foundation back in 20 years ago. I went to their first conference in 2007 and saw Steve Coase, the OpenStreetMap founder, presenting the first results where he'd mapped a few of the streets in London and a few elsewhere. And I remember thinking, this guy's daft. This is never going to take off. They're never going to get anything useful, any kind of useful set of data for this. But actually nowadays, the OpenStreetMap includes almost all of the transmission lines in Europe. So not just road maps, it's also mapping electricity infrastructure. And we use it as a basis for our grid modeling. And Open Energy Transition got this MapYourGrid project funded. I think Tobias Augsburg is leading it. And that project is really to extend the grid mapping to all regions of the world. So there are some regions of the world that aren't so well mapped, and that lack of information and data on their grids is a bit of a hindrance in doing studies for their decarbonisation. So one really good way you can get involved is either funding the MapYourGrid project, or also if you can volunteer and help map based on satellite data. There's very good instructions there on MapYourGrid to help you contribute towards the data in OpenStreetMap on electricity infrastructure.
Wow, so we have a sliding scale of things you could possibly do to kind of achieve liberation from fossil fuels for this, and a kind of greener grid for the world to be running on that may be useful for green software, but also may be useful for kind of humanity and society on Earth, basically, by the sounds of things.
Yeah, totally. You absolutely have agency. You can choose where you host your websites. You can choose which companies you're using for your AI services. You can look at their accounting, how they've been doing the accounting, and vote with your feet, or get involved in the modeling, get involved in the mapping. Those are all things that everyone can get stuck into.
Tom, thank you so much for coming onto the call. I've been looking forward to doing this for ages, and I'm really, really glad we finally got around to getting on the call together. Have a lovely day, mate. And thank you once again for joining. We'll make sure that we've got loads of really nice, juicy links for people for this. If people do want to know about you and your work, or follow you online, or where should people be looking? I just have that as a final closing note.
Yes, so I have a website with a blog, and I usually also, share thoughts on LinkedIn and occasionally on Blue Sky. So those are the places: blog, LinkedIn, Blue Sky.
And hopefully I'll catch up with you soon in the summer, in a nice beer garden in Berlin or Brandenburg soon. All right?
Looking forward to that. Let's do that. Thanks, Chris.
Okay.
This is really fun.
Hey everyone, thanks for listening. Just a reminder to follow Environment Variables on Apple Podcasts, Spotify, or wherever you get your podcasts. And please do leave a rating and review if you like what we're doing. It helps other people discover the show. And of course, we'd love to have more listeners. To find out more about the Green Software Foundation, please visit greensoftware.foundation. That's greensoftware.foundation in any browser. Thanks again, and see you in the next episode.